Before we start Module 6, I want to briefly motivate why we are switching topics now to material degradation and time to failure. We had our first introduction to a probability distribution in Module 4, and we learned about normal distribution in Module 4. We learned standard normal distribution tables. We also learned to use software such as Octave to do our manipulation of normal distribution calculations. Then in Module 5, we saw an application of normal distribution to doing probabilistic design as opposed to deterministic design. In traditional deterministic design, we would have a deterministic strength value and a deterministic load value, and we would choose a factor of safety to account for the uncertainty in the strength value and the load value in traditional design. But in probabilistic design, we would characterize the intersection between the load probability curve and the strength probability curve, and you would characterize through that interference between the load and strength curves the desired reliability, and you design to achieve a desired reliability. So we ended Module 5 with a detailed example, and we saw that with a little bit more, it involved a little bit more calculation, nonlinear calculation, to solve for our unknowns. You would usually have at least two equations, one specifying your design parameters mean value, and another specifying your design parameters standard deviation, and then using the two equations, one for safety margin and the other for load roughness, or through specified coefficient of variation, you can solve for those two unknowns. Now, we're going to explore other probability distributions, and they will come in modules 7 and 8. But prior to moving on to the other probability distributions, we want to first motivate that in engineering problems, oftentimes the time to failure in reliability context, the time to failure is the uncertain parameter. And why time to failure is an uncertain parameter is because of material degrading with time. Okay, and that's a consequence of second law of thermodynamics. And we will motivate that, and we will start with simple models to describe times to failure in Module 6, and then we will go on to other more common models to describe times to failure, probabilistic distributions that are commonly used to describe times to failure. But whatever we would do in Module 7 and 8 are motivated in Module 6. As I said, degradation is fundamental to all physical systems, and it's a consequence of second law of thermodynamics. Entropy will continue to increase with time, and that's again a result of energy that we put into systems that are not recovered, or other dissipative processes such as diffusion that occur in most systems. Reaction, oxidation, diffusion, all of these are entropic mechanisms. So examples of mechanisms where you have degradation with time are creep, fatigue, oxidation, corrosion, wear, electromigration, stress migration, dielectric breakdown. All of these are examples of entropic degradation, consequence of second law of thermodynamics. In terms of time, how product failures occur over time, for most products, empirically, we observe that there are three phases in the life of a product. Most engineered products have three phases. And the first phase, where you have a decreasing failure rate, And that's the portion that we call as infant mortality or early failures. And then you have part where the failure rate is nearly constant, but it's random. And that is the useful life. And then as the product nears its end of life, you've reached the design life of the product, and then you have an increasing rate of failure, and that is the wear out stage. And this curve is called the bathtub curve. It has a shape of a bathtub, and this is empirically observed in nearly all the products. Usually, the infant mortality phase, the early failure phase, where you have decreasing failure rate, are a result of escapes into the field due to manufacturing defects. Manufacturing defects that have escaped into the field. And as these defects cause failures, and as you exhaust all the defective parts that have escaped to the field, your rate of failure will decrease. And then you reach the useful life portion. And then as you reach the limit of your design, you start seeing increased failure rates. And that is the wear out portion. So you see this empirically. And what we would like to do is to model these three phases of any product: the early failure phase, the useful life phase, and the wear out failure phase. You'd like to model them, and you'd like to find a mathematical form to describe these failure rates. And we will judge whether a particular mathematical model, a probability distribution is a mathematical model from a reliability perspective. We will judge whether a probability distribution or a mathematical model is adequate if it can capture these three phases of a product life. We don't have to have a single model to capture the whole life of the product, but you need to be able to capture each individual phase with any mathematical model. That's how we will judge whether the model is adequate or inadequate. And going forward, we will judge our probability distributions against this criteria. Can it model the bathtub curve, the phases in the bathtub curve? It doesn't have to model the entire bathtub curve, but it needs to be able to model the decreasing failure rate phase, the random constant failure rate phase, and the increasing failure rate phase. So a simplest model that one can think of to describe these three phases of a product life is a power law degradation model. And it's a simple power law form where S naught is some initial parameter value, and A naught is some material dependent constant. M is another material dependent constant as well. So S is some parameter of interest to us. S, as we will see in an example that we will work out in module 6.2, could be the thickness of the oxide layer, or how far a part is corroded, the thickness of the corroded portion of a part. And S naught might be the initial value, and then you look to see how it either increases with time or decreases with time. So depending on whether you use your plus here, sign here, or minus sign here, this could either increase with time or decrease with time. Normally, when we want to characterize these and fit to a form like this, we would linearize them. Fits are always better in linear form than in this sort of a nonlinear form. When you in order to linearize curves like this, what we would do is take the log on both sides. So here, for instance, I would move S naught over to the left-hand side. So I would have S minus S naught over S naught. So I'd take care of the 1 inside the parenthesis, and then take log on both sides. And this plus or minus sign is included inside the log, because if S were to be less than S naught, then you have a decreasing parameter value with time. and the minus sign would take care of the negative sign associated with S minus S naught, and it will lead to a positive value. If, on the other hand, if S were to be increasing with time, S minus S naught would be positive, and you would use the positive sign. And when you fit this, the slope will give me my M, and the intercept will give me my A naught. And that's how I can describe this sort of a degradation with time. And in a nutshell, this is what we would be doing with more sophisticated probability distributions, such as log normal and Weibull, which we will cover in modules 7 and 8. So let's consider decreasing parameter with time, the form that you would have. That's the power law form. That is the linearized version. And you can see the plot of S naught minus S over S naught as a function of time. And you can see how the parameter is decreasing with time. And you can see what happens when you have different M values. Okay, so this is M equals 1. This is a larger M value, M value of 3. And this curve corresponds to M value of 6. And same in now, if I plot in the linearized version, you see that in the log, if I plot log of S naught minus S over S naught against log of time, what I find is that these are straight line curves. And this concept of linearization is very fundamental in probability distributions, and we will use them extensively when we do data fitting. It's very important to linearize before you do data fitting. So here is the same power law model. This is a power law model, but for a parameter that is increasing in value with time. So this is a linearized form, and the plots for various M values. Now, another important physically important quantity that we should characterize for any given degradation model is the degradation rate. And you can see here the degradation rate divided by 1 over S naught, that normalizes it, has this form here, M over Ts, T over Ts, but Ts is a scaling parameter here. So previously we had A naught, we had parameter A naught, but when we expressed it in the power law form, we used a scaling constant Ts. And because that's much more physically intuitive for us, A naught is not as intuitive. So that's the reason why we chose to express it as Ts, because we know Ts has units of time. It's a scaling constant. So now you can look at the degradation rate. The degradation rate has this form, T over Ts to the power M minus 1. The key point to observe here is this power M minus 1 here. So what that says is that when M is equal to 1, the rate will be independent of time, or rate will be constant. That's an important point to observe here. When M is equal to 1, the rate will be constant. When M is greater than 1, the rate will increase. When M is less than 1, the rate will decrease with time. Those are important observations. And we have a minus sign and a plus sign here. So the minus sign is for decreasing rate, or ds by dt being negative. When ds by dt is negative, you'll apply the minus sign. When ds by dt is positive, you will have the positive sign. So the rate is always positive. Okay, that's a key point to observe here. This rate is always positive. Okay, so now let's look at the rate of degradation plotted as a function of time for various M values. When we see for M less than 1, M equal to 0.5, we find that the rate of degradation is a decreasing curve. So this form can be used m less than 1 can be used to model the early failure phase of the bathtub curve. When m is equal to 1, then you have a constant failure rate, and that can be used to model the middle portion of my bathtub curve. And m greater than 1 gives me the form that I can use to model the wear out portion of the bathtub curve. So in other words, this power law model, the simple power law model, has features that can capture the various portions of my bathtub curve. Now you could say, well, in my product, I have a delayed start of degradation. This is just a mathematical convenience. It's not fundamentally introducing new physics, but it's just a mathematical convenience. You can introduce another offset parameter T naught, so that you model not from time t equal to 0, but from time t equals T naught. And so you model the growth or decrease from time t equals T naught. And therefore, then you get a 3-parameter model. The 3 parameters would be, previously we had 2 parameters, Ts and M, that described the growth. Okay. And usually you can notice here, we would only have Ts and M. Previously, we only had Ts and M to describe the rate. Now we would have Ts, T naught, and M to describe the rate. So this becomes now a 3-parameter model, and this 3-parameter model might better fit to the data. It's just a convenience. And then once you have a model like this, you can define failure as time it takes to reach a critical parameter value. So I might have a critical parameter value S sub f, at which I might declare the product to have failed. For instance, if I have a layer that's growing in thickness, when that thickness reaches some critical value, I might say that's no longer acceptable to me. That's my failure parameter value. And whatever time it takes for me to achieve that failure parameter value is the life of my part. So that's how one can describe time to failure. Now, alternatively, you can say I have a useful life. So I have a time to failure, and I can find the parameter value at that time to failure, and that would also describe my expected parameter value at end of useful life. So that's introduction to material degradation models. So I introduced this idea that things degrade with time. Therefore, often in reliability calculations, its time of failure is our uncertain parameter. And we would like to find mathematical forms that best describe this time of failure. We know that normal distribution is not a good model simply because normal distribution extends from minus infinity to plus infinity, whereas time to failure only goes from 0 to some infinity, some large value. And the simplest time to failure parameter degradation model is a power law form, and we'll come up with other forms in module 7 and 8. So with that, I will end module 6.1.